Welcome to today's lecture. Today we're going to be reviewing our next lab, which is Lab 6, and then getting into malloc, specifically malloc and malloc with structures. So I'm going to break this week up into at least two lectures, and the first lecture here today I'll introduce malloc and we'll use it for some simple data types as well as some aggregate arrays. The next lecture then will cover malloc and structures. Okay, so you're going to need both of these lectures in order to complete the lab as well as to be comfortable with last week's instruction on structures themselves. So for the lab, what you have to do here, it's a relatively simple lab. I don't provide a template or any code to get started, but the program really isn't going to be that long. What you need to do is create a structure that can hold this data here, so a type, a file name, and access, and it's highlighted, it's spelled out here in the description of the file. Inside of your main then, you're going to create a pointer to that structure. You'll malloc memory for that structure, read in the data to populate those members of that structure. Don't print anything off in main. Then for the second part, you'll declare or you'll create one function. The function will have a pointer to that file structure type, and then you'll pass that structure to that function and then print it off in the function. Okay, so we'll go over everything you need in order to complete the lab, but as usual, if you run into any questions or if there's any ambiguity, please let me know, send me an email, and I can certainly help put you in the right direction or correct the lab so that it maybe reads a little bit easier. Okay, so to not waste any time then, what we'll do is we'll jump right into malloc. So what is malloc? Malloc is a function that we use in C to dynamically allocate memory. And as we go through some of the sample code here, I'll do my best here. Let me get this full screen. I'll do my best to really highlight what the differences are between and why we'd want to use a malloc. Okay, it's dynamic memory allocation, and so what that really boils down to for us is that when we run a program, we don't allocate memory in the program until we need it, and once we need it, we use malloc to request memory from the system, from the operating system. Malloc is going to request the memory in bytes, and so we'll talk about how we determine the number of bytes we need in order to make an appropriate malloc request. Malloc is good because it's dynamic, and that provides us the ability to make our programs a little bit more efficient. It's a little hard to maybe see the value of that early on because most of our programs that we're writing are relatively small. They're not consuming a lot of memory, and we have, for most of us, laptops and smartphones and tablets, things that have multiple gigabytes of memory. Obviously that wasn't always the case, and C programs run on a variety of different systems as well, where memory still may be a limitation. So it can become a very powerful tool to be able to dynamically allocate memory in your program. The first thing that we're going to look at here is just a definition of the function itself. And so part of getting into programming is being able to take something, a function, like our malloc call, like our malloc function here, and read something like this to figure out and understand what it does. Okay, so this came from Tutorials Point. It's a website that I like to use in order to pull up function definitions or function prototypes, essentially, of C functions so that I can understand what they do. There's a couple of things here we need to know. Obviously, we need to know the name of the function, which is malloc, and we knew that. We need to know the type and the number of the arguments. We need to know its return type, and then we need to know what is the description about it. Okay, so as far as what does it do? Well, it allocates the requested memory and returns a pointer to it. Okay, and we knew that just by looking at it because we can see here that this is a pointer. This is how we define a function that returns a pointer. In this case, it's maybe a little strange because it's a void pointer. Okay, we don't typically associate the void keyword with returning anything, but there is such a thing as a void pointer, and we'll talk about that here in just a little bit. The next thing is the argument. Okay, so there's just one single argument. It's a size_t in size. Why is it size_t? Because it's an unsigned integer. We can't request a negative amount of memory, so we're always going to request a positive amount of memory. What this says here, it doesn't say anything about bytes, but the bytes are going to become important because we're going to pass to the malloc call the number of bytes that we want. Oh, I'm sorry, it does say it right here. Okay, the number of bytes that we want in order to use in our program. Another thing that you need to be aware of is that the function returns a pointer to the allocated memory. That's good. So what's a pointer? What's the value of a pointer? It's a memory address. So if we have a successful call to malloc, we get the memory allocated to us that we requested, then we are going to have a memory address to that memory that was just allocated for us. If it fails for some reason, it's going to return a null value. Okay, and I'll go through that in some of the code here to try to show you how we would check to make sure that if our pointer, if the return type from malloc doesn't have the memory, if the malloc call failed, we cannot proceed. As you continue to work with pointers, and also now we start working with malloc, segmentation faults are probably going to encounter those quite a bit. Segmentation faults just means that you've ran off into memory somewhere that you do not have permission to. You're trying to access a memory address that has not been allocated to your program, and that's what oftentimes will result in a segmentation fault. So when you run into a seg fault, look at your pointers. If you can't figure out what you're doing wrong, just start commenting them out. Basic troubleshooting, comment them out until you can identify where the trouble code is, and then identify it from there. Overall, we're going to cover here quite a bit more as we move into this discussion about malloc. So, you know, instead of providing you a bunch of small lectures this week, I'm just going to provide one big one, well, one or two big ones, and so this will be probably quite a bit of information here in this lecture, much more so than what we've done in the past, the last few weeks. So, you know, I just encourage you to download the code, follow through as we're going through it, and, you know, stop and digest it. Maybe watch the lecture once or twice, or specific parts if you struggle with. And again, if you run into anything that you just don't understand, or I'm not explaining clear enough, just let me know. I'd be more than happy to work with you directly, or, you know, produce another video that maybe helps clarify what I'm trying to get across. Okay, before we can use malloc, we need to figure out how many bytes we're requesting, right? So the purpose of malloc is to dynamically allocate memory in our programs, and when we call malloc, we provide as the value to that argument, that one argument that it has, the number of bytes that we need. Well, how do we determine the number of bytes that we need? Well, we have another function called the sizeof, and the sizeof helps us determine the number of bytes that we need. Let's stop right here, and we'll look at some code. Okay, so you'll see I've uploaded, I just called it sizeof.c. At this point, I have my standard includes. I'm even including string.h. I don't think I'm using it, so I could probably get rid of that. But then this is just a simple program, right? We're gonna enter into main, and we're just gonna print off a few things. So if we look at sizeof, what does sizeof do? Well, it returns the number of bytes that a variable needs. So in this case, we're going to print off the size of an int, the size of a float, the size of a double, and the size of a char. Now, what you have to understand with this is that it's not the size of the size of the variable itself, or the value in the variable. It's how many bytes has the system allocated for any variable of these types. Okay, these are all primitive types. So when you declare an int variable, the system will allocate a certain number of bytes to store the value of that variable in. It doesn't matter what value actually gets stored in there, it's going to allocate that same amount of bytes every time. So when we say size of int, what we're asking the operating system, what we're asking the system to tell us is, how many bytes do you reserve for the int type? Same with float. How many bytes do you reserve for the float type? Same with double, and same with char. Okay, so I'm going to comment this out, just keep the output a little bit uncluttered. Compile that program, and we'll run. Okay, and there's our output. So what you see here is that every time we declare an int variable, the system will allocate a reserve, 4 bytes for it, regardless of what we store in it. 4 bytes get allocated for it. 4 bytes for a float, 8 bytes for a double, and 1 byte for a char. So as you've worked through programs, we probably haven't used too many programs that are going to hold very large values. But this is the reason why a double is going to store more data, a larger value, than an int, because a double has more memory allocated to it than an int does. This is why an int has, we looked at those max, those symbolic constants for max and mins. This is why they exist, because an int can only hold, it only has so much memory available for it to store information in. Okay, so that's it. If we put size of and we pass any of those data types, then it'll return the number of bytes needed in order that are going to be reserved or be allocated for it in the program. Now, it's important that as you start to figure out, you'll say, well, 4 bytes for an int, and that's pretty common, right? But there's the potential that not every operating system is going to use 4 bytes. And so it's tempting to, instead of using the sizeof call, to just use 4. And we'll look at that in the code, but the reason we don't do that is because not every system allocates 4 bytes for an int. Some systems might do more, some systems might do less. For the class, it doesn't matter too much because we're all using Ubuntu or Linux, most of us anyway, if you're in the IA lab, and so we all pretty much have the same setup. But just knowing that going forward, it is a portability issue, and that's why we're always going to use the sizeof operator. If we look at declaring a variable, okay, there's a couple things I want to point out here. The first is the sizeof. Okay, so with this, we use the sizeof on the type itself. Okay, 4 bytes for an int, 4 bytes for a float, 8 bytes for a double, 1 byte for a char. Here, with this printf, you can see that we're going to do the sizeof on the variable itself. So we've declared an integer variable I, and I've just initialized it to a value of 99. Then in here, this printf does the same thing we did up here with these 4 printfs. It just prints off the sizeof, but instead of using one of those data types, we use the variable itself. Because I kind of jumped over this, I just want to make sure I'm clear on the format specifier. If you look at this, that's the format. That's just the tab character. Okay, that's just help align the output. And then here's our format specifier for a long integer. And that's all that is. All right, so let's go back and we'll recompile that code, and we'll run it. Okay, so there's our original output, and now here's the size of I. Okay, 4 bytes. So that's telling us, we already knew that. It's telling us something we already knew. That is that the system's going to reserve 4 bytes for any integer variable. Okay, we could do the same thing with the float, and we get the same results. If I change this value, okay, something considerably larger, and we go back and compile, and we run that again, you see still 4 bytes. Okay, so that is how we use the sizeof. We use sizeof to tell us how many bytes are needed, so that when we use malloc, we can give it an accurate number to dynamically allocate that memory. Let's see. The other thing I wanted to say, and this goes back to that kind of the why we use malloc. When we take a program, even something as simple as this, and when we compile and run this program, what happens when this program runs is that the compiler, or not the compiler, I'm sorry, but when this program runs, the memory, the 4 bytes of memory that are needed for this variable, they get allocated at runtime. So before we enter main, before that actual line of code gets executed, the operating system knows that we've declared an integer variable called I inside the, well, it doesn't necessarily know it's I, but it knows there's an integer variable in here, and it allocates the memory for it right away at runtime. That is much different than what happens with malloc. With malloc, you'll see, we'll declare a pointer, but we won't get the memory to store anything in that pointer until we've run the program. We dynamically allocate that memory. So what I'm trying to get at anyway is that even something as simple as this memory, this 4 bytes of memory that get allocated when this program runs, they're tied up for the duration that this program runs. When we use malloc, we only tie up the memory as long as we need it. We request it, we use it, and then we release it. We deallocate it or we free it. And again, we'll go through all that process here in a little bit. All right, so there is our sizeof operator. Okay, so going to the void pointer then. There's a couple things we need to talk about with the void pointer. One is that the function itself, malloc itself, returns a pointer to void. Okay, it's going to dynamically allocate memory, and it's going to return a memory address to that memory that's been allocated. It does this through the void pointer. Now, what does the void pointer mean? Well, it doesn't. It's a pointer, but it doesn't have a specific type. And so when we go through the code, you'll see that we're going to typecast that void pointer. We're going to typecast that to the type of, the type of data that the pointer is eventually going to point to. There's a couple things that you need to keep in mind as we're using the void pointers. We start working with the void pointer. And that's really these last two bullets right here. Okay, when you assign it, does not require a cast when assigning. Okay, so when we assign a pointer the return value from our malloc calls, we don't have to typecast it. I'm going to show you. I'm going to typecast it. All my code is going to typecast it. I'll show you exactly what that means and where we're doing that here in just a few minutes. But I will do that. You don't have to, but I will. When you dereference it, though, it does require a cast. Okay, and I'll walk you through both of that in code here in just a little bit. So just keep that in mind as you're working through it. If we go back to that sizeof file, then you'll see there's another section of code. And what I'm going to do is I'm going to comment this out just so we can focus on the appropriate output. Okay, get rid of that straggler there. All right, so if it returns a void pointer, then that means that the void pointer is a type. And we can declare a variable that is a void pointer. We can declare a pointer that is a void pointer. That's what I'm doing right here. So we can, just like we've declared other pointers, you have the type, in this case it's void, and then we have our asterisk. And our asterisk just has to come somewhere in between the variable name and the type itself. Okay, so this is a variable, a pointer, that is a type of void pointer, or void. So it doesn't have a specific type. This next 3 lines of code then is what I want to show you is that because it's a void pointer, we can assign it any type of value that we want. It does not matter. It will not generate any errors. So in this case, what we have is we have an int variable called A, a char variable called B, and an array, an integer array of 40 elements. Okay, the values there are all irrelevant. What's important to look at is the type. This is a primitive. It's an int. This is a primitive. It's a char, and this is an aggregate. It's an int type. So they're all 3 very different types. These next 3 lines of code, though, 24, 25, and 26, you can see that I'm assigning the memory address using the address operator. So right here, I'm assigning the memory address from each one of these variables to that void pointer. And what you're going to see, although I don't generate any output with this program right now, what you're going to see on the output is that there's going to be no errors or warnings. So no errors or warnings. Now, normally you would have an error and a warning. So let's say that I declared an integer pointer. Okay, so I use int, and then I'll just call it iPointer, and I'll set it equal to 0. Now, if I wanted to assign, that's a pointer that's going to point to an integer data. If I wanted to assign to iPointer the memory address of that char, I'm not sure if that's going to error out actually. Let's see what happens. Okay, yep, it does. So you get this warning. It's a warning. This program's still compiled. You just get a warning here, but it says assignment from incompatible pointer type. So that's the error that we get. I'm trying to assign to an int pointer the memory address of a char. Okay, and I'm doing that right here. But you see with that void pointer, it didn't generate any warnings, because the void pointer, you can assign it any data type you want. All right, I'll comment that out, and I'll leave it in the code that I upload just for future reference, just so you guys can see that as we're talking through. Let's see, if I want to dereference a void pointer, then what we have to do is we have to typecast it. So let's say that I want to simply print the value of A. A is an integer, so we'll use the format specifier %d, and then we'll dereference a pointer. Okay, the next thing I'll do is we'll just comment those out. And the only reason I'm doing that is so that my void pointer is a pointer. I just want to assign it the memory address of our integer variable A. Okay, so we'll just get rid of that, and let's compile this and see what happens. All right, we get an actual error there. Say warning. Well, there's a warning and an error. Warning dereferencing void pointer, and error invalid use of void expression. Okay, and it points at the line. So what does that mean? Well, that means that we didn't typecast it. And we'll talk more about typecasting when we start talking about malloc. And typecasting is not something that we specifically covered. And one reason was just because I knew we'd get to it eventually, and I wanted to introduce it at a time that we're actually going to use it. So this is that time. This is part of one of those reasons that I said this lecture might be a little heavy, because there's a lot of things we need to talk about. So what does typecasting do? Well, we're not going to get into the nitty-gritty of it. You just need to understand that it temporarily casts the type of a variable to a different type. Okay, so if the void pointer is nothing, it's not any type, then that means when we dereference it, C has to understand what type it's referring to. Okay, in this case, it points to an integer, but it's still a void pointer. So when we do this, the system, what's running this program, doesn't understand that it's pointing to an integer type. So that's what those errors are telling us. It's like you're trying to dereference it, but I don't know what it points to. I don't know if it's 4 bytes for an int. I don't know if it's 1 byte for a char. I don't know if there's 8 bytes for a double. It doesn't understand. And so when we typecast, what we typically do is, actually I think we need to do that right there. We wrap in parentheses. So in this case, you can see we have a parenthesis here and a parenthesis here. We wrap in parentheses the type that we want to cast something to. So what I'm saying here is that my pointer, I want to cast into an int pointer. Okay? And that's what this is telling us right here. You can typecast anything. Take any of those primitive types, type it in there, and that's what you're going to typecast. The problem, well, it's not the problem, but the catch with typecasting pointers is that you need to tell it that, hey, this a pointer is an integer pointer. And so when you need to typecast the pointer, then you need to use the type plus that little asterisk. Okay. Let's see if this actually works, or if I may have made a syntax error. Yep, made an error there. Let's see here. There we go. The value of A is 44. Okay, so that maybe looks a little confusing, but what I did is, let me back this up just a little bit. Okay, so what happened, why I was still getting an error when I did this, I'm trying to typecast, but I'm not typecasting appropriately because there's this order of precedence, and essentially what's happening here is that I'm trying to dereference the pointer and then typecast it. I need to typecast the pointer first and then dereference it. So we use those parentheses to establish that order of precedence. We say do the stuff inside the parentheses first and then work your way out. So in this case, let me go back to the way I had it that works. So in this case, I'm saying typecast my pointer to an int pointer and then dereference it. I'm not sure if I need those extra parentheses, so I'm going to take those out and let's just see if that compiles. I'm not sure if it will. Yep, it does. Okay, so that works too. Value is 44. Okay, it never hurts, in my opinion, it never hurts to use the parentheses. If anything else, it helps to clearly identify the order of precedence that you're trying to get out of your code. But in this case, this works. Okay, we typecast the pointer, then we dereference it. Okay. All right, and we'll do this a lot with malloc. Okay, this is just a point. This is just a good point to talk. A good place to talk about it. We'll continue to use it. We'll be using typecasting and pointers. They get to a point where you just, even if you don't fully understand it, you're going to be able to just do the same thing over and over again with our malloc calls, and hopefully that makes sense. All right, so let's see, how long did that take? Well, 24 minutes. All right, and we're finally ready to move into malloc. So let's take a look at malloc. And all right, so malloc is dynamic memory allocation. And what you're essentially doing then in your program is you're saying, okay, I need some memory. I'm going to use malloc to request the memory from the system, and the system will do one of two things. It'll either say, yep, I have those number of bytes available, here's a pointer, here's a memory address for you to use, or it'll say, nope, I cannot allocate the memory for you, and returns null. Okay, so there's the only two options you have when using malloc. We have a combination of things then that we tie together in order to use the malloc itself. So when we look at this sample code here, this little screenshot, malloc returns a memory address. So all of the variables that we use, all of these variables that we use with malloc calls are going to be pointers. Okay, so you can see here that what I've declared is a pointer called p that's going to point to integer data. Now we have our malloc call. We have one argument, right? So we have to provide it the number of bytes, and then we have our typecast. Okay, this typecast, if you can remember anything else, it's always going to be the same as the type of the pointer. Okay, remember this right here is optional, but I'm always going to do it. I'm not going to leave any room for error or ambiguity in my program. If you don't do it, that's fine, but there's no hard and fast rule that says if you search that on the internet, you'll find plenty of conversation and discussion about which way to do it. But just know I'm always going to do it because I believe it to be a best practice. So it's always going to be of the type that your pointer is going to be. Uh-oh. Pen's not working. Okay, well, I guess we'll just move on. And that makes sense because malloc is going to return a void pointer. Okay, if it allocates the memory, it's going to return a memory address. But at this point in time, the malloc call doesn't know anything other than you just allocated whatever you provide as the argument. Let's see, I got to get this working. I wonder if my battery died on me. Okay, well, I'll try to use the touchpad. It'll be a lot harder, but I'll try to do it. So when malloc returns that void pointer, we're telling the system, we're telling it at runtime that pointer, that memory address, that what we're going to store in that memory is going to be integer data. It's going to be an integer, or it's going to be an array of integers, whatever. So what this code is, this is an integer variable. That's all it is. So int asterisk p. Sizeof. Okay, something we need to talk about here is that you always want to use this format, the size of, and then the type of the data that you want to allocate. Okay, we know after running that last program that an integer is 4 bytes, and so it's tempting, if you look here at this bottom, to just say, well, why shouldn't I just malloc 4? If I know it's 4, why call this extra stuff and just say 4? Just provide a value of 4 in here. And the problem with that is you can do that, and that'll work. But as I talked about earlier, if different systems implement different sizes for their memory, your system might depend on this being 4 bytes. If all of a sudden it's 2 or it's 8 or it's 10, it can cause unexpected results in your program. This way, using sizeof, it's always safe. You'll always have the correct number of bytes for your program to make sure it works. All right, so we've talked about most of this already, but now we're looking at it actually in a little more code. Okay, again, here's a call to malloc. We're going to, this pointer is going to point to integer data. Okay, so we typecast the return value from our malloc call as an int pointer. Okay, these things will always match up. And then we do the size of the int. Okay, and this will give us, through the use of a pointer, through our p variable, 4 bytes of memory, or enough memory to store 1 integer value. All right, and we'll look at some code here in a second. So this is just another example of that. Keep in mind, this is a pointer, right? So if after you've allocated memory for this variable p, you want to do something to it, you need to treat it as a pointer because it is. So if you want to assign a value to it, you need to dereference it. P is a pointer. The value of a pointer is a memory address. It points to that allocated memory that you want to store the value in. So in order to store that value or access that value, you have to dereference it. And then keep in mind, again, we'll look at this in code, but just keep in mind that malloc returns null if the memory is not allocated. I can't think of a time where it's happened to me, but if it does, then, and you don't handle that, if your pointer returns null and then you try to do something with that pointer, odds are it's going to generate a seg fault. So it's just, again, it's a good practice to get into to make sure that that's not the case, to make sure that that pointer that you assign the return value from a malloc call to has an actual memory address. It's not null. Okay, so we'll get to arrays here in just a second. And let's look at some code. So the second file that I'm going to upload is, I'm going to call it structures in malloc. And we're going to look at this file in well, we might break it up into maybe 3 parts even, just due to the length of this lecture right now. We're going on 30 minutes, so I'm going to wrap this one up pretty quick. I'm going to have a lot of commented stuff out, but we are going to talk about all of it. So we'll use this file for everything that we covered. Okay. Look at our includes just to make sure. I always do that just as a sanity check for myself to make sure that I didn't miss anything. A lot of commented stuff out. Okay, we're going to look at these functions and using structs as our argument types. And we'll use this structure here in a little bit, just as an example. We'll talk about this function as well, probably in the next lecture. So this is going to turn into a 3-part lecture. And then here's our main. Okay, and I try to comment everything that I'm doing in here just so you understand. And I kind of put this in a bad order. Okay, so unfortunately I have to comment the first couple of things I want to do. We already looked at this, but I just want to look at it again because now, well, we've looked at something very similar, but I want to look at using our variables now with malloc in an actual code, an example, in a sample program. These previous 2 lines are how we declare arrays, and you'll see that it's pretty straightforward. So if we want to declare, when we looked at that sizeof program, okay, and we looked at what does it take, how much memory do we need for an integer variable. Okay, and we did that with this printf right here. The size of an int will get 4 bytes. Okay, and we used our sizeof with that data type int to figure that out. So when we want to declare an integer variable, well, we just need to use malloc. We'll have our sizeof an int, and we'll make sure that we declare a pointer. So in this case, it's an integer pointer, iPointer. That's how the naming convention I came up with in my head. It's going to point to an integer data type, and then we typecast it. Okay. Once we've done that, then we can dereference that pointer and assign a value to it. And if we want to access that value, okay, in the case of this simple printf here, using a format specifier %d, I can dereference it and print it. Okay, so we'll go and we'll compile that program and see what kind of output we get. Okay, what did I get? Okay, so I got an error, a pointer. All right, and what happens is, you see here, there's a bunch of code that I have not commented out, and so the error was that I'm trying to use this a pointer variable before I declared it because I just commented it out. So I'll get that cleaned up, and now we'll go back and compile. Now we're good to go, and if we run that program, okay, there you see the value of iPointer is 99. All right, so that's all it takes to malloc memory for a variable. Okay, we can do that for anything. If I want to have a char pointer, okay, it's going to be the type. It's going to be a pointer that points to a char. It's called C pointer. I won't typecast this one just to show you that you don't have to. But then I'll do size of a char. Right? If it's just going to be a simple primitive variable, I'm going to point to a single char. Then I just need to do the size of a char. Okay, I'm not typecasting that. We'll compile it. We didn't get any errors and any warnings. Okay, so that's perfectly legit, but I like to typecast. Like I said, I don't want to leave any room for ambiguity, because what happens if you don't typecast it, then C itself will figure out based off of this assignment the type that it should automatically be casted into. Is that a problem? You know, probably not. But again, I just find it for myself at least to be a best practice to just not leave any room for error. Okay, I want this to be typecast to a char pointer, so I make sure that I do it myself. In this case, once we've done that, this becomes a pointer to a char type, so we treat it like a pointer. You can dereference it to access the value. It's a pointer. You can access the memory address to pass it to a function. It's just a pointer at that point. Okay. Let's see. Let's go back and I'm going to skip ahead just a little bit. Okay. All right. So what I'm going to do is we're going to talk about free, and then I'm going to wrap up this lecture. I'm going to provide an additional lecture where we'll talk about arrays, using malloc and arrays, and then finally what I'll do is provide probably a third that deals with structures in malloc. So this will be again kind of a long week, but we'll all get through it. So dynamic memory allocation. When you dynamically allocate memory for something, once you're done with it, it is critical that you deallocate it. And so we have to use a call to free. Okay, so you can see here, we need to free it. It has one argument, and that is the value. It's a pointer to a previously allocated chunk of memory with malloc. Okay, this is the important thing to remember with free is that you can only use the free function on memory that has been dynamically allocated. Okay, we're going to look at malloc, and we'll talk about calloc as well, and then there's some other ones. Okay, but it has to be one of these dynamic memory allocation functions to call free on. You can't call it on anything else. So how does that look in our program? Well, in this case, let's say that I'm done with my I pointer. Okay, that's all I have to do. Okay, we declared it here. We malloced memory for it here. I did some stuff on line 29 and 31. I'm done with it. Now I can free. That deallocates the memory. That takes that memory, in this case, those 4 bytes of memory, and it just says to the operating system, here you go. Here's your 4 bytes of memory back. I'm done with them. You can now allocate that memory to some other program. Once we've freed it, you can't use this pointer again. Once it's been free, if you want to use that pointer, you need to malloc memory for it again. Okay, so once it's been free, you call free, you have to make sure that you're absolutely positive that you're done with the memory that you have allocated to that pointer. All right, and if we go and run the program now, even though we free it, again, you're not going to see any changes. It doesn't generate any output. The program doesn't behave any differently. It still runs just fine, but the dynamic memory has now been freed. Okay. All right, so that is the basics of malloc. Okay. We use pointers, so we declare a pointer like we have been. We malloc memory, and we determine the size of, or the number of bytes that we need. Once we've done that, we can typecast, because malloc returns a void pointer, so we typecast that void pointer into the type of data that our pointer is going to point to. So this will match this, and now we have a pointer that points to whatever number of bytes we just dynamically allocated. I did say what happens if malloc fails. Okay, so here's an example of that. I'm going to modify this just a little bit since I'm making a little bit of changes to the flow. So I have I pointer, and what I want to do is let's actually move this up because it's important. Obviously, I'm using that pointer before I'm testing to see if we got the memory allocated for us. So I'd want to do something like this. I'd want to try to malloc memory for it and then immediately test. If I pointer is equal to null, then do something, right? At this point, if we're in main, if we return 1, that means that something that the program didn't finish successfully. It terminated abnormally. If we just return, we're in main, same thing. We're done, we're fine, we can get out of there. We can return 0, or maybe you want to try to allocate memory again. It's completely up to you at this point. The important part is, though, that if after trying to malloc memory for it, if it has a null value, you don't want to do something like this. Okay, if you do something like this, it'll probably turn into a segmentation fault. Okay, so it's important that you just simply test that pointer for a null value. Okay, and in this case, again, we can run the program. I haven't run into an issue where malloc has failed. Let's see, there's an error on line 30, and that's an easy one because I forgot the if. Okay. Okay, so no errors, and if we run the program, you'll see that it still ran just fine. All right, so again, that's the introduction to the pointer and using pointers for primitive types. The next lecture will cover pointers and arrays, and then for the third part, we'll look at using pointers and malloc and pointers for structures. So, all right, thanks.